What about the laser point? And this
one, yes.
Among everybody, and we have the organizer for the heavy work they've done to organize this conference, and of course the participant who had the long trip to come here. And of course I was rather fortunate in this sense because my office is within 1 kilometer from here, so I was lucky. Now, we will ask yourself why the title is in French, but as we are discussing with Sandy Fetter yesterday, every language is some subtleties, so it's hard to translate sometimes from one language to the other. And, sorry?
Not après, it's Alexandre Dumas.
You know, the culture people, obviously. All of this. Okay, so indeed, so why this title? No, this way, why this title? Let me tell you first that this was done with the Fabrizio Palestinism, and it just appeared in Israel in the archive last week. And the reason why, well, there are three relevant lengths for superconductivity. One is the intra-pair coherence length, just the correlation, which is a single Cooper pair, if you want to say it. The other one is the hidden length. We use this unfortunate name phase because the broken symmetry is in the phase. And this will be the correlation between different Cooper pairs. And of course, since those are two independent quantities, you should compare with something. And the only other quantity you can compare with is the interparticle distance. The first paper, as you can see, was published 20 years ago with Fabio Pistolesi, who, by the way, is now in France. And was my first paper in this business. And 2 years later, we also published the paper on the hidden length. And was only t equals 0, but was the first paper to concern about the whole crossover from weak coupling to strong coupling. Okay, so these are the results from that time. I think I should take this. So it's only t equals 0. Along the crossover, now already Chris Ray has told us what this parameter is about. This is the two-body scattering length, and it's negative here because there is no bound state in the two-body problem. It's positive here because the bound state has already entered. This is, of course, a many-body problem when it's a finite density. And the two lengths in the BCS limit, very weak coupling, the two lengths are essentially the same. I let it to be parallel to each other because since they come from two independent calculations, two independent definitions, there is always a factor of 2 or pi or whatever if you do independent definition. That's why they're proportional to each other. But you see, close to unitarity, they start to differentiate each other. And then the key feature of the crossover, that all the degeneracies are really removed. And one of them, which is just the size of the pair, becomes smaller. I'm sorry. Okay. Yes, becomes smaller and smaller at the when you go to the bosonic limit, whereas the other one has a minimum close to unitarity, and then it is going to start increasing toward the bosonic limit, because to heal some damage of superfluidity, you need long distance to do it for the weakly coupled boson gas. Okay, so you've already seen a picture. Here is why it's 20 years later, like in the famous romance by Dumas. And actually, the three characters here are very unlike what I'm going to say, because this guy was mostly interested in the two-body things. Okay, so the intra-pair correlation. This guy was mostly interested in organizing the whole the whole business. So the overall organization, and this guy had to do the dirty work. So. That's essentially why. So this is a very, very simple reminder of already Case Ray has is already told you very schematically. So very quickly, I have only a couple of simple cartoons about this crossover. So you want to pass from the situation where you have non-interacting or weakly interacting fermions and just fill up at Fermi C up to the Fermi level. If the interaction becomes so strong that those guys form molecules, they essentially return to collapse into the lowest particle state. And so with this crossover, you can pass continuously from one situation to each other, and the parameter, as I told you, those will be the two extreme limits. Here, the scattering length is negative, no bound state has occurred yet, and here is positive, and pictorially, this is what I have in mind. In one limit, there is no distinction between inter and intra-pair coherence. I'm sorry, it's terrible. Okay, so there is no distinction between interpair and intrapair coherence length. On the other limit, those molecules are tightly bound, and there will be a mutual correlation between those molecules. And that's why the two lengths will differentiate each other. In the intermediate interesting limit, which is a unitary limit, essentially the interparticle distance and the pair size becomes comparable, and this is the unitarity limit, which is so famous in 3D, but of course not in 2D. And we are going to comment more on that. So with this in mind, with this target in mind, now we want to extend what we did at t equals 0 to final temperature, up to very large temperature, or above also the Fermi temperature. And I will show you that with this target in mind, along the way, we are going to, discover something which is interesting and understand probably better what we have done before in those 20 years which have passed in between. Well, when you want to go above the TC, of course, you have to go naturally beyond the field, and therefore you have to include Perry fluctuations. And this is the simplest way to include Perry fluctuation. Brave people are welcome to improve on this approximation if you'd like to. And so you see you have repeated two-body scattering, but this will be in the medium, so it will be a finite density. So there will be essentially a many-body problem between opposite spins. And if you want to, you can construct a self-energy out of it. If you want to, you can go one step further and construct the response function. And that's by taking the functional differentiation, you get the density of state diagram, the Azonato-Lacan, the Mackey-Thompson diagram, and so forth, from which Andrea Volano was talking yesterday. This is a general problem. When you start reading any book on superconductivity, the first sentence is about, well, in superconductivity you have a correlation between fermions with opposite spins, but that is the end of the story. I mean, there's nothing much more than that. So in general, let's see how those two lengths can be defined. So this pair correlation length is obtained from the pair correlation function. And the pair correlation function is just the probability if you have one particle with spin up at, say, r equals 0, to have another particle spin down at a certain distance. So you see here we have already introduced two different quantities, which is the relative quantity, and this will essentially be important for the internal wave function pair, and this is the central mass quantity, and this will be important for the correlation between different pairs. And you see, we have subtracted the trivial non-interacting terms here just to have only the interaction parameter. These are field operators for spin up and spin down, and of course, if you have a homogeneous system, the dependence on capital R will drop down. And so, since these quantities well behaved, at least for the case we have been looking at, you can define a characteristic length in this way, by taking those probability averages here, and you extract a characteristic length. You can do it for any temperature and any coupling as you want, of course, within approximation and consider. Now, how is the Hilbert length defined? The Hilbert length is a little bit more difficult because you have two inputs. in a sense. You have to introduce the correlation functions between pairs. So what we did is the following. You have a pair operator. So you have a pair operator here. And we notice a strength of attracting function. Why? Because if you average this composite field onto the state of the statistical ensemble you are going to consider, you want to get the gap function. Okay? And this for a homogeneous system will be independent. Then you are going to construct the component of this composite field, which is along the stiff part of the Mexican hat. Okay? So not along the easy part, but along the stiff part of the Mexican hat. And then you're going to define the correlation function between those quantities at different space point and time point. And for convenience, we take only the zero frequency component because it makes an average picture of the system. So what is nice here, and I think I like it a lot, if you are above the critical temperature, of course, we did also a calculation below the critical temperature, with a single diagrammatic structure, you can construct both functions, both the function which is a pair correlation function from which you can extract the pair length, and also this correlation function between the gap of the order term at different points from which you extract the hidden length. You see, and the minimal ingredients that you can really introduce in the many-body diagrammatic theory is just the series of these cross diagrams. And by just taking the variables which are different at the end point, you get the two correlation functions. So with single theory, you get both. So you, at the cell level of approximation. So I think it's nice. So let me tell you the main result, okay? So we learned some physics out of it. At short distances, with this approach, we get what is known for the pair correlation function, what should be okay for the pair correlation function. So you see, it has essentially the two-body physics when the two atoms come close to each other. So there is this characteristic dependence on the distance square, and only in the linear term you have the interaction parameter coming into, and the coefficient probably is the best definition of the task contact that Chris has mentioned before, because apart from this 4 pi square, the coefficient in front is just identified with the task contact. And the task constant from this sort of approach, or this sort of definition, is the interface between the two-body physics and the many-body problem. It's just the coefficient which really plays the interface here. And of course, you can calculate this task constant in different way. Of course, we have calculated from this approach, and we have compared with our previous calculation where we have started from the tail of the momentum, the distribution function, and those numbers count perfectly into each other. So universality is confirmed also at the numerical level. But it's also nice that you can learn some more, because if you now make a rather heavy calculation, you just calculate the spatial oscillation, the spatial structure, or the pair correlation function, you get some information about the underlying Fermi surface, of course, if any, because in the bosonic limit you expect the Fermi surface to be gone. And this is what we get here. So here are the we take this pair correlation function and multiply by rho squared to avoid that singularity as small r, and we plot it as a function of the interparticle or the distance between these two fermions for different coupling. Here it will be unitarity, here closer to the BCS limit and closer to the BEC limit. So those dots are our numerical results independently obtained for each value of rho, and then we have tried to fit those results with this form here, which shows you some oscillations with a characteristic vector Kc, and also some overall exponential decay. And you see, if Kc is 0, there will be no oscillation is cosine term will just be a constant, and it will only have the exponential decay. So we did this calculation for a number of coupling, and we got this result here. So this is the characteristic wave number plot against this parameter, this interaction parameter. Here is unitarity, and you see the Fermi surface essentially collapses here. We have compared this result with the totally independent calculation, and Andrea Perai was heavily involved in that. And it's a calculation where you get from the analog of the ARPES spectra in cold atoms, which is the angular momentum resolved for photoemission spectra. So you get another independent wave vector which tells you, you see this is the Fermi wave vector here, and it really is going to decrease, and it collapses at the same point. Totally independent calculation. Two independent calculation tells you that the wave function, I mean the Fermi function, the Fermi surface is collapsing here. And this is a message for Chris Wave. This, I think, is more important. Sorry. This feature here about the collapsing Fermi surface, from the conceptual point of view, is more important than this unitarity link. The unitarity link is only a two-body problem. This is a many-body physics, and will unify two-dimension with three-dimension. We have actually a manuscript which is still unpublished with Frank Marsilio. We test you that the more fundamental quantities in this sort of physics, and which is also important for how this is squared or not, because those are two-dimensional problems, is the collapse of the Fermi surface. Okay, unitarity is something nice because you can save some numerical effort if you want to, but it's not the fundamental issue in this sort of physics. Okay, so those are strong statements which will be essentially independent of the particular approximation, the simplest approximation we are taking, because people can improve on that, and the numerical value will be different, but the general framework will be the same. So it's important to say that pair correlation function crosses the critical temperature with no damage. So it will essentially be a final value, and it will pass through essentially in a regular way. And after that will be a decrease in functional temperature. Then you will expect. Well, at very high temperature, where the virial expansion will be valid, we know that T-metric approximation is becoming a good, an excellent approximation. So the result we got with this particular approximation would be essentially the correct one. And this is also something very natural. What else can it be? The pair correlation function is limited by the thermal wavelength. So essentially you have the thermal fluctuation makes an earthquake in your system, and the correlation can be seen only within this length. I mean, they can, of course, as you see, they are always 4 pi or pi square root of pi, the definition depends on this sort of thing.
Sorry, this is also true in the BCS limit.
It's true everywhere.
But the BCS limit, you said xc squared is like df over delta, so it's dc to the left.
Only a few 1 0, I guess.
No, I'm sorry. Let me do just one more step, okay? Just be patient. So this those are two different lengths, okay? So this is a pair length, okay? So the size of the pair, and the one will be correlation between different pairs, okay? Now it comes, okay?
So
those two people are anticipating the business. Okay, so here is, okay, so here's the other length. It diverges on both sides, I mean, when you approach the C. And when we can also calculate it in an analytic way, it will become smaller than the pair coherence length for large temperature, because you have in addition this, this logarithmic term where the thermal rent also appear. So the two lengths are going to cross each other, because one is going to be very big close to critical temperature. It's going to become smaller at high temperature. There may be should be, there has to be a characteristic temperature where those two are crossing each other. Yes. Well, I call it T star, but that's but you can call it T pair, I mean, or T over bar, or T tilde. That doesn't mean there's any characteristic temperature. And here are some examples of what I'm going to say. And this is also asked for other reasons. This is the heating length, which diverges at critical temperature. That's what it was. And it diverges at any time. Of course, the critical temperature is going to increase. When temperature is increasing, and therefore the whole thing shifts to the right. This is the pair length, which is a finite value, and it goes smoothly at Tc. And it's also nice. You see, the more you increase toward the molecular limit, the more it becomes flat. Okay, so it's something else. And you see, there's a characteristic temperature, but the two processes. And this temperature is moves to a higher temperature the more you proceed to the BEC limit. So you can, this star, or whatever you want to call it, represents a crossover temperature where independent pairs, which are correlated over a length-side pair, get correlated with each other. Okay? And if you plot it, if you do this calculation for many, many couplings, you see something interesting. So this will be the critical, temperature. I'm sorry. Okay, this will be the critical temperature within this theory. The blue line will be what we got here as T star, where those two lengths are crossing each other, and the dotted red line will be what you would call the BCS critical temperature within the BCS limit. And I had to apologize because I have not understood what he meant for so many years, because it's something silly. I mean, it is, whereas here now I know. Essentially now this slice gives the physical meaning to this temperature, because essentially is the temperature where the pairs are organizing themselves. Okay? 5 minutes, okay, sure. And yes, and there's a curiosity here, and of course you can learn a lot by a curiosity. This is the heating length as a function of temperature below Tc for different couplings, okay? For different couplings. And those curves are two independent calculations, no fitting parameters. Just a single rescaling function, which were a factor, which is square root of 2 or 1 over square root of 2, because they are two independent calculations, so they get two independent definitions of the quantity. And you see they just go on top of each other. One of them, those dots, are obtained by making a very accurate solution of the Boglie-Urdagen equation, or you make an imprint of a vortex, okay? So you do a heavy calculation, heavy numerical calculation, and you measure the size of this vortex in a very accurate way. So it will be mean field, okay? But for the inhomogeneous situation, inhomogeneous field, okay? So that's the message I want to tell you. Here will be fluctuations, corrections, because you have to do this correlation function, but for homogeneous calculation. So this is something very interesting. You see, the inhomogeneous mean field has already knows already about the excitation of the system. So knows more of what the homogeneous mean field will know. Okay, and this is something interesting. Now, the conclusion, come to the conclusion. And the conclusion are, we have implemented the concept of the wave function of the Cooper pair at any temperature and any coupling across the crossover, distinguished from internal wave function at the central mass wave function. We have presented a description in terms of minima diagrammatic structure. Of course, if you want to do more, you're welcome on that. But I'm sure it's already had the work, which englobes these two concepts in a rather unified way. And also, finally, we'll give a very well-defined physical meaning to this crossover temperature as a temperature where those pairs are organizing themselves. And therefore, precursor pairing phenomena can show themselves below this temperature. Of course, in the meantime, between 20 years ago and today, we learned a lot, and therefore this time has not passed in vain. But did we forget something? Well, those two people are absent now. I mean, what did we forget?
No, when we were asking, this was done in 3D, or does it depend on the
It's the 3D.
But does it depend on the equation of the conventionality or not?
We didn't do the calculation too deep. Okay. So what did you forget? You got this guy. Thank you for your attention. Does anybody ask what is this guy?
No. The questions can be asked in French as well.
I can
Let's start from somebody else in the. Thank you.
You presented a nice determination of this characteristics of momentum.
Yes, so you can speak louder.
So you presented the determination of the transitorism momentum for the collapse, which characterizes the collapse of the first surface. Extracting it from this Bell distribution function. So it depends if you directly calculate the Fermi momentum distribution. So in principle, okay, that means that a step it's a smoother Fermi surface, at least in the BCS limit, and then it gets smoother and smoother. But
Yeah, there's something about that's there's no random.
yeah,
So the message here is that Fermi tries to resist as much as possible. It's a strong concept. Fundamentally. And it's actually so strong. Okay? So we check it with two totally independent calculation and the result of equations. Single time experiment. And this is
I have some problems with your traditional use of side pair, using the pair correlation function.
Yes.
Because so you take the pair correlation function and you integrate the space with phi square. So the pair correlation function at large distances is dominated by phonons, and this is 1 over r to the power 4.
We don't have phonons here.
Okay, so
Okay.
but I mean, on
Sure, sure. So here goes multitude and what they also do. Okay? Yeah, but of course you can isolate those two behavior. Short range and long range. Yeah, but we don't have
Yeah,
phonons.
because
By construction,
in your approach, you are sensitive only
No, no,
to
no,
single
no,
character excitation, not the phonons.
not all the things. No, the phonons.
Well, okay.
Okay. Chris?
Just a simple question. This point where you say the Fermi surface disappears, is that simply the point where at zero temperature the chemical potential is no longer...
It's close by, so you cannot do that.
Thanks. Giancarlo, if I will make mapping of your approach to the conductivity, so Xi pair, this is BCS coherence. Xi phase is as small as my integral. But why at the BCS side of the crossover, Xi phase is smaller than Xi phase? I would expect vice versa.
On the BC, I mean, T was it? No.
At the figure I saw, Xi phase is smaller than Xi pair.
It was above TC.
No.
This
is a picture above
this.
TC.
A picture above TC.
Ah,
Very high. You see, they cross it at large.
Okay, so this is a pseudo-gate region.
Sure.
Okay.
So it was. So I mean, where this crossing is this time, it shows
Okay, here,
Just for the understanding, I mean, the collapse of the Fermi surface is something that comes out of your population.
Yes.
You
Or
interpret
different
that,
calculations.
you interpret that as the onset of bosons in such a way that the Fermi surface disappears.
Well, of course, when the system becomes fundamentally boson-like, there's no need of research. So if you are the system, normally that's the key concept.
Okay, any more questions? You have
Well, yeah, my question is general. So you apply the T metrics and you say the best way to attack the problem. I don't have a better way, but it's, you didn't explain exactly when this should be break down this is a perturbative method in a problem that in principle you cannot apply for superphysics.
No, I didn't say that. My saying was a bit different. I say it's the simplest way to do this calculation. Of course, you want to improve on that, but I said that for instance, the high temperature is exact.
Yeah, that's
okay. So this crossing, of course, if you do a better calculation, this crossing really is different. So I'm looking forward to other people to do it in a different way, but the physics will be the same.
When you mean physics, you mean?
I mean, one has to the verter very close to the figure. It has to go to this molar, and the other one does not do it. And large temporal will be the same, so there must be something. Of course, if you get a 10% difference in this time, you will very much, you will be very much well.
Okay,
Okay. So let's thank